Welcome to the GE Modern INU demo video presentation. In this presentation, we will cover team members, the problem statement, the constraints and specifications, the impact of COVID-19 on the project, a performance summary, challenges, and key design features. The team members are Taylor Hagg, the team captain, Addison Jensen, the point of contact, Kyle Schwark, the secretary, Nigel Armstrong, an electrical engineer, and Robert Gardner, a computer engineer. Our faculty advisor is Professor Scott Zeidema, and our sponsor contact at GE is Matthew Alberta. GE currently makes an initial reference unit that provides navigation data to vehicles. The current IRU no longer meets the precision required. Our task is to integrate a new fiber optic gyroscope and GPS receiver to provide more precise navigation data over Victory Protocol communication. The project is summarized by GE's vision statement for the project. Adversaries have developed effective measures to compromise the GPS service by degrading or denying positioning, navigation, and timing solutions. The Modern INU project will develop a new Army capability for persistent, high-accuracy PNT among the diverse ground and airborne assets that collaborate to prosecute a mission. Constraints regarding the project involve the handling of information and data, since some of the data is ITAR-sensitive information. The design must minimize size, weight, and power. The design will be powered via a 28-volt DC battery. The design must meet mil specifications for shock, vibration, and temperature. Lastly, the design must output position, navigation, and timing data over Victory Ethernet protocol. Unfortunately, due to COVID-19, all meetings had to be held over Skype. The project scope shrunk to virtual design and documentation only. Building a physical prototype was not possible due to COVID-19 restrictions. Some challenges included handling sensitive data, integration of new and existing systems, software optimization, hardware optimization, and quality documentation. Now, let's look at some key design features. A total of 3 Flex PCBs were designed for the Modern INU demo. The J1 Flex PCB was modified from GE's existing PCB design. Altium was used to import the Gerber files and reverse engineer the rest of the design. Shown here is the J1 Flex PCB. The purpose of the J1 Flex PCB is to connect the IRU to the outside world. The term J1 refers to the 66-pin circular connector shown here. The Flex PCB connects to the existing IRU card through the 59-pin connector shown at the top of the Flex PCB. Unfortunately, the existing IRU card that this connects to cannot be shown in this presentation. The Flex PCB was modified to accommodate the Ethernet switch. 2 male RJ45 connectors were added and can be seen on the left. This allows the Ethernet signal to pass through an Ethernet switch. The Ethernet signals were routed using over-under differential routing. Most connections were left unmodified from the original GE design, only the length was extended to accommodate the new mechanical housing. A terminal block was also added to the design to allow 28 volts to be connected to the Ethernet switch. The terminal block can be seen just below and to the right of the 59-pin connector. The Daughterboard PCB presented multiple challenges to our design team. Using a 256-pad ball grid array for mounting, the board could not be much larger in dimension than the ball grid array it mounted to, limiting space to 1.5 by 1.5 inches inclusive of an edge keep-out region. Due to the small size, routing had to be pre-planned and components really only had 1 or 2 positions on the board that would work. Shown on the board is a microcontroller, pulse transformer, 25 MHz crystal oscillator, flyback diode protection IC, 5-pin programming port, and a variety of chip capacitors and resistors. All components had to be surface mount due to the board mounting situation. Routes for the crystal oscillator were kept as short as possible to minimize inductance and ensure accuracy of the clock. All Ethernet traces were routed with a 100 ohm differential pair impedance. The lines within each differential pair were within 1% in length of one another to ensure signal timing was correct, far exceeding the normal requirements for Ethernet routing. Power comes from GE's IRU board through the ball grid array, but all incoming 3.3 volt power for components on the daughterboard first pass through a capacitor bank. This is done to ensure even delivery of voltage as current draw changes in use. This and all other PCBs were designed in Altium and are indicative of our team experience in designing PCBs. The Adapter Flex PCB was designed from scratch to enable the interfacing of a new GPS with GE's existing GPS Flex PCB. As part of our specifications, the Modern INU demo would need to be compatible with the old GPS receiver that is on the current equipment and the new GPS receiver for use in this demonstration. In order to accomplish this, the existing GPS Flex PCB needed an additional route for higher voltage power to the GPS pins. From here, either the old GPS receiver or the Adapter Flex PCB and the new GPS receiver can be installed to provide GPS and precise timing data to the INU. Routing was not particularly challenging with either the GPS Flex PCB or the Adapter Flex PCB, but special care was taken to minimize impedance changes along the transmission lines. By following this practice, we plan to eliminate reflections. The FPGA has three main functions. Firstly, routing the PPS timing signal to the daughterboard MCU. Second, the FPGA receives the position, navigation, and timing data from the IRU processor. If the address on the address bus for the SPI module and the write enable is high, then the FPGA will format the data into a package with its address and store the package into a FIFO buffer. Lastly, the FPGA will send the position, navigation, and timing data to the daughterboard MCU over SPI communication. This occurs at the same rate that the information is written to the FPGA. The module is written in VHDL in the Xilinx IDE. An SPI module was designed first. This image displays the SPI test bench where the package sent out is simulated looping back and being received using only the MOSI line as shown where the TX package is equal to the RX package. Next, a FIFO buffer was created to store the package from the IRU before being sent. This image shows the FIFO buffer test bench. Lastly, not displayed due to confidentiality concerns, are the modifications to the GE program to allow for the routing of the position, navigation, and timing data to the FIFO buffer. The daughterboard MCU has three primary tasks: retrieving PNT data from the FPGA, generating a Victory Protocol compliant XML file containing the PNT data, and transmitting this data to the Victory data bus via UDP sockets. The MCU will utilize FreeRTOS in order to manage these tasks. Usage of the FreeRTOS also provides the daughterboard MCU with a scheduler, enhanced multi-threading capabilities, and allows for the use of software devices such as semaphores. The software used to monitor the contents of UDP segments examines them on a per byte basis, which is not visually appealing. This is a formatted sample of the contents of the UDP segment transmitted from the daughterboard MCU to the Victory data bus. This is the initial declarations and position service portion of the Victory Protocol compliant UDP segment. The mechanical portion of this project was to combine the current top hat assembly shown with a new inertial unit that was chosen by GE. The gray adapter plate shown was designed to allow for these two components to be combined. This adapter plate houses the Ethernet switch as well as provides a space for external exposure of the J1 connector. GE also requested that the current top hat assembly be able to house either the current GPS receiver or the new GPS receiver chosen by GE. The mounting holes in the current top hat assembly do align with the mounting holes on the new GPS receiver, and therefore adapter brackets shown were designed to use the current GPS receiver mounting holes and allow the new GPS receiver to mount to adapter brackets. A 28-volt DC-powered 4-port Ethernet switch is housed inside the mechanical design, which allows for Ethernet communication between the FOG IRU processor, the J1 output, and a debug monitoring console application developed by GE. The Ethernet switch is rated to operate anywhere from 5 to 30 volts and will receive 28 volts from the J1 flex connector with a maximum power consumption of 1.1 watts. The Ethernet switch has internal reverse polarity protection in the event of an improper power application. Alternative power rails on the IRU processor card were considered, but availability of the 28-volt DC input rendered it the preferred choice. Now let's recap to see how all of these components work together. The system will receive 28 volts DC through the J1 circular connector on the outside of the housing, which is routed to the existing GE IRU card and Ethernet switch through the J1 Flex PCB. Power is distributed to the rest of the components through the existing IRU card. Once powered, the GPS and fog will start functioning, outputting navigation and timing data to the IRU card and the FPGA. The FPGA will then format that data and send it to the Daughterboard via SPI communication through the internal routing of the IRU card and the 256-pad ball grid array. The MCU on the Daughterboard will then format the data properly to be sent out on the Victory Protocol Ethernet bus through internal routing on the IRU card to the 3-row 59-pin connector on the J1 Flex PCB. From there, it will pass through the Ethernet switch and out through the circular 66-pin J1 connector and to the console application if desired. Fortunately, we were able to complete the design and meet all specifications. Some parts were ordered at GE's discretion, and the project provided unique and valuable engineering challenges to the team.